So we're going to have a chat about compounds and surface finish. We will have a chat about compounds and aesthetics. We are going to better understand what kind of parameters is affecting the surface finish of molded parts. How did we develop this very tricky topic? We wanted to create a lab experience and the design of experiment. So we are going to introduce the topic in itself and see what are the parameters affecting the formula and injection molding, and how will we discuss the quality of the surface finish and aesthetics with the molding design of experiment. So we were going to actually play with this topic by fine-tuning some parameters in the formula and in the injection molding process. We will conclude our webinar with a wrap-up, trying to better understand how it is possible to make technical compounds, injection molding, and all the parameters working in both fields, injection molding and plastic formula. First of all, we have to try to define what is aesthetic. Outcomes that we are talk about aesthetics even when we are talking about technical plastics. You know, technical plastics are normally not conceived for fashionable applications. So why are we talking about aesthetics and technical plastics? Because even when we're working with technical plastics, we are having issues with surface finish and how parts appear. We need to have a perception of a finely working and perfectly working, finely molded part. And it is absolutely very important to keep an eye on the aesthetics and surface finish, even with the most complicated and the most high-performant compound. So if we want to define aesthetic, it's a bit philosophical, but aesthetics is defined as the set of elements dealing with the nature of beauty, art, and taste. So you read no plastics in this sentence, but beauty, art, and taste. I want to play it big, so I introduced this picture of this nice statue. Why did I do this? Because the search for beauty has always been in the mind of man since the early ages of our civilization. Beauty is a very tricky mixture of different perceptions. You see how this statue is actually made out of different materials and the different proportions between the parts of this body. How do we perceive, how do we feel beauty and aesthetics? First of all, we see it with a visual perception. So we will appreciate a smooth and uniform appearance, just to give you an idea. Or with our tactile perception. For this reason, we will appreciate a smooth feeling on a glossy surface and a rough feeling on a rough surface. And we will not appreciate any roughness on a glossy surface or any glossy area on a rough surface. Last but not least, we must not forget the olfactory perception. If you have the most beautiful looking piece of engineering, but it smells bad, then you will have a bad perception of that very part. All these nasty issues with the perception of beauty can be summarized in the plastic part showing up here. You see how this part can be absolutely perfectly performing, can work perfectly great, and injection molded with the most performing technical compound, but it looks bad. It looks poorly molded, it looks full of streaks, the color is not even, the surface is rough and not glossy. You have the perception of a bad looking part, but you also have the perception of a poor and poorly working part. And this must be absolutely avoided when it comes to technical compounds. Now let's see what is a compound. We have already been talking about this quite a number of times, but it is important to talk about what is a compound even from an aesthetic point of view. A compound is a mixture between a base resin, which is the polymer, which is the plastic in itself actually, and a set of additives that we put into this plastic matrix to achieve some specific performances. First of all, functional additives, talking about flame retarding agents or self-lubricant agents or thermally conductive agents and so on. Then you have fillers providing dimensional stability and mechanical properties like glass fibers, carbon fibers, mineral fillers, and we will see some of them during this webinar. Then you have plenty of processing aids. Compounding, extrusion, calendering, and injection molding are extremely demanding processes requiring a lot of processing aids as lubricants, stabilizers, nucleating agents, detaching agents, and you name it. We put plenty of these into our compounds to have a perfectly working plastic. Then you have stabilizers of any kind. Heat stabilizers, chemical stabilizers, UV stabilizers, thermal stabilizers, you name it. And then, of course, you have pigments and everything providing a good-looking aspect to our plastic. Colorants, pigments, laser marking additives, printing aids, and so on. When it comes to aesthetics, it is important to keep in mind that each one of these will provide its contribution to the final surface finish of our injection molding part. And we have to look for a compromise between performance and surface finish. Today we are going to have a chat about the effects of different base resins, of different fillers as mineral fillers and glass fibers. This is the topic that we are going to discuss today. We have seen the compound, but what else is also affecting aesthetics in an injection molded piece of plastic? Of course, it's a very complicated process. So even the injection molding process will provide some effects to the surface finish and to the quality, aesthetic quality of our part. First of all, the barrel temperature. The barrel, you keep your melt material in the injection molding machine. Then you have the mold temperature, which is the temperature of the tool where you inject your plastic to create your manufacts. And then you have the injection speed. That is the speed used to inject melt plastic into the tool. These three parameters are extremely important to achieve the aesthetic level we want to achieve. What happens if the temperature of the barrel is too high? If the temperature is too high, we will have flashes. It means that the plastic will be too liquid and will just be squeezed between the two halves of the tool. Or you can actually destroy the material in itself. If the barrel temperature is too low, you can run the risk of having a short shot, which is a not completely filled part. And it's absolutely a no-no. You do not want to deal with that. What happens if you have a too high mold temperature? Bad issues. You will have the part sticking to the tool. It will be almost impossible to detach it, even because the shrinkage will be higher and the part will be completely glued to your tool, and you will have issues. Of course, you will have longer molding cycle because it will take a lot of time to cool down, and it is a problem. If the mold temperature is low, you have a short shot as well. You can have releasing issues as well, and you can also have other aesthetic issues that we are going to find out during this webinar. If injection speed is too high, you can run the risk of having flashes or having overpacking or having bird marks. What does injection speed mean? It is the speed that you apply to your melt plastic to fill the cavity. When you apply a high speed, you are also applying very high shear stresses to the polymer, which can actually be destroyed by these stresses. It becomes more fluid, it can create some gases, you have a very bad mechanical performance of the part in itself, and you will have absolutely a poorly performing and a very bad looking part. So you want to stay away from too high injection speed. If injection speed is too low, of course, you run the risk of having short shot or even having insufficient packing. I want to focus your attention on the fact that these three parameters are not the only ones affecting actually the aesthetic of your plastic. You also have the filling pressure, the switchover time, and the packing pressure. Packing is really very, very important. Packing is the pressure and the time that you apply when the cavity is full to properly pack the plastic polymer into the cavity. Of course, we cannot analyze all the effects of these because it would be an endless design of experiment, and we want to put it on a much easier way. We are going to focus our attention on injection speed, mold temperature, and the previous formula exceptions. Keep in mind that aesthetics is a compromise between mechanical performance, between processing time, between molding cycle, price, and so on. So you have to find, you have to finely tune your process and your formula in order to achieve the best compromise between a good-looking part and a perfectly performing part, which can also be attractive from a market point of view. The design of experiment that we are going to see today is designed to achieve the best looking, the best aesthetics. Some other parameters affecting aesthetics. Of course, you have injection location and the type of injection. Injection is the part of your molding equipment where material flows through to fill the cavity. It is very important, the place where you put it in your geometry and the shape of your injection system. Ejector location. Ejectors are the pins used to push the molded part out of the tool. And it's very important where you put it because they can leave a sign on the freshly injection molded part. The color shade is extremely important. We will see that our eyes perceive aesthetics in a completely different way, even depending from the color of the part in itself. Our eyes are extremely sensitive to any kind of defect on dark colors, and they are more tolerant on light colors or chroma colors like deep blue or deep red or stuff like that. So dark shades are a bad issue when it comes to aesthetics, because any defect, even the smallest defect, will be immediately detected by our eyes. Last but not least, the texture. A glossy surface can be extremely difficult to achieve if you want to have a perfectly looking part, but some glossy or some matte surfaces can be tricky as well, especially in the case of extremely fine matte surfaces. In that case, even the slightest scratch can really look terrible. We are going to focus our attention on the injection location and type. We will see two different injections set up. We are going to see only black parts because black color is the toughest when it comes to aesthetic and surface finish, and glossy parts because glossy and dark is the hardest combination when you want to discuss aesthetics and surface finish. Just to give you an idea, I put these two parts below here. They are exactly the same geometry, molded with the same material but with two different colors, and you can actually perceive how different is our sensation when it comes to color, to beauty, to aesthetics. The part on the right seems perfect, the part on the left looks awful, but it's the same material, the same tool, the same injection condition. It is just a different color. So you can easily understand how hard it is to achieve a perfectly looking part. Let's talk about the tool that we are going to see work with today. It's a kind of bowl, a semi-spherical bowl with a perfectly polished surface. It's a glossy surface. You have the moving side on the left where you put all the ejectors. You have the fixed side. Of course, you have two types of injection, as I already said. The first injection type is a fan gate, which is placed on top of the bowl, of the semi-spherical bowl. And the second one is a submarine gate, is a 3-gate submarine nozzle. We just change the nozzle and we can simulate the effects of a fan gate and a 3-gate submarine gate. And you will see how effective can be a proper selection of the best injection location and the best injection type. Now, let's start from the very beginning. Let's see how the part can be filled by using a finite element simulation. What you see here is a mold flow simulation. You can see how even is the filling path when it comes to filling this bowl with a fan gate. Everything runs smooth, there is no welding lines, the part is filled like a charm, everything looks perfect. And now I want to focus your attention on what happens when you use a 3-gate submarine injection system. Yeah, that's it. If you, let's put it here, you see what happens in this situation. In this situation, you can see how the 3 flows can weld in one specific location. This will lead to a specific fiber orientation and will lead to weld lines. Weld lines are a major issue when it comes to the surface finish and the quality, the aesthetic quality of your part, because we will see how bad can look weld lines. So since the very beginning, we see that a 3-gate submarine injection system and a fan gate injection system can perform very different from the very beginning. The submarine gate, multiple gate locations will lead to a lot of weld lines, and the number of weld lines is even higher if your part is not simple as this one, but it's a bit tricky with holes and stuff like that. Each time your melt flow must turn around a hole, you will have weld lines. So pay attention to weld lines and pay attention to the way your part is injected and filled. Now we have seen the tool, we have seen the injection that we have selected, we have seen the geometry that we have selected. Let's give a look at the materials that we are going to play with this afternoon. So the first material is a polyamide 6 with 35% mineral filler. We will see what's the meaning of mineral filler. We will play with 3 different mineral fillers, and we will see how different is the effect of 3 different mineral fillers, even if the formula is exactly the same on paper. The second one is a typical metal replacement plastic, polyamide 6,6, 50% glass fiber. Is a super performer, outstanding mechanical performances, very tough, very resistant, very dimensionally stable, very tricky when it comes to aesthetics and quality of the surface finish. The last material we are going to play with is a very nasty one. It's a polycarbonate, so it's an amorphous resin filled with 30% glass fiber. We will see how complicated it can be to have a properly looking amorphous material filled with glass fibers. Amorphous resins are perfect, work great in many applications, but they can be a bad bond when it comes to aesthetics and surface finish. These are the materials. Let's see the molding conditions that we have set up on our injection machine for our design of experiment. For the polyamide 6 35% mineral filler, we have selected 250 degrees C for the barrel temperature, 255 for the nozzle, and 80 degrees C for the tool temperature. Very typical injection molding condition. We will keep the same molding condition for all of the materials that we are going to test this afternoon. Then we have polyamide 6,6, 50% glass fiber. In this case, the molding conditions are exactly the same that we use on this kind of polyamide 6,6. So 280, 285 for the barrel and the nozzle, and a tool temperature of 80 degrees C. For polycarbonate, we wanted to keep a bit open when it comes to the tool temperature for a reason that we are going to find out during the last design of experiment. All the rest is typical. This is the typical setup for amorphous polycarbonate. Now let's jump into the design of experiment, and let's see what happens and how the surface finish is affected by the parameters that we have seen right now. So by injection location, injection type, different formula, different injection speed, and different tool temperature. First of all, let's focus on what is a mineral filler. We have tested 3 different mineral fillers. Talc is a typical mineral filler, providing normally outstanding surface finish and outstanding dimensional stability. As all mineral fillers, the drawbacks are concerning impact resistance. They are not great performers. Then we have Wollastonite. Wollastonite is a very glass fiber looking mineral filler, so you have outstanding mechanical properties. You know, the Wollastonite is looking like spikes, so it actually performs a bit like glass fibers, and it's very hard as a drawback, so it can actually create some wear on your equipment. The last mineral fillers that we are going to talk about is kaolin. Kaolin is a cheap mineral filler, which is very interesting from a mechanical and a chemical point of view, but it is quite hard, quite difficult to properly disperse in your compound. So we are going to see some issues related with the dispersion of kaolin in our design of experiment. So these three guys here are the mineral fillers that we are going to check with this polyamide 6. Let's see what happens. Let's start from the very beginning. Let's start first material, polyamide 6, 35% talc, injected with 3 different speed. First of all, with the fan gate. So with the fan gate, our bowl will look dull using a low injection speed. So you see that the quality of the surface is not really acceptable. It's dull, is slightly rough. What happens if we move up with the speed? By increasing the speed, so by increasing the shear stresses and the temperature of the melt, thanks to higher injection speed, you see that you have quite an improvement on the surface, but you still have some issues close to the injection location. You still have some spots here and there. So you see that your aesthetic is improving with the same material, the same geometry, the same injection location. You can improve your aesthetic, your surface finish, by increasing speed, and you can achieve a very good, excellent result on our polyamide 6 35% talc by using high speed. You see how different is the gloss of the surface. On the picture at left, you see nothing. On the picture at right, you can even see the hands of our technician and his cell phone taking a picture of that, just to better understand how glossy and how reflective this surface is just by working on injection speed. This is an extremely interesting and really outstanding result, I would say. Now let's see what happens on the other side. We have seen it on the, let me say, on the curved side. Let's see what happens below. The same stuff. You see the same trend, so you have a very bad looking nasty spot below, which is looking even worse at medium speed, but it will completely disappear by increasing the speed. So with the same material, with the same geometry, with the same tool setup, you can actually achieve a perfectly looking surface finish just working on the injection speed, moving from a low speed to a high speed. High speed means higher temperature of the melt. This is something that you must not forget. Speed is always related with stresses, and stresses are always related with temperature. Temperature increases as stresses increases. Now let's see what happens if we swap the injection system and we put in place the 3-gate submarine. Remember, this is a design of experiment, so we want to perfectly understand which is the role of each factor that we are going to tune in our equipment. If we apply a 3-gate submarine injection system, you will see that the surface is always dull, so you have always a very opaque surface, but you see that around the injection location there is something different popping up. There is some kind of spots, something that you have not seen before. You have some kind of lighter areas, and you see the weld lines. You see those lighter, more glossy surfaces evidenced by the small lens. That's a weld line. And weld lines can be extremely nasty. They can look really, really bad. if we increase the surface, you will have if we increase the speed, you can have a much better looking surface, but you always have evident spots around the injection location, just like the case before. The situation is perfectly solved if you increase speed. You have an improvement, but you still have some kind of weld lines. So pay attention to weld lines when it comes to different injection location. Let's see the same from below. Also in this case, you see the same trend. So you see a much worse looking surface, which becomes dramatic in the case of a medium injection speed, and they disappear, or I would say they more or less disappear when it comes to higher speed. But please look how you still have some kind of sign here, you have a sign here, you have a sign here. So something is different between the fan gate and the 3 submarine gate. Pay attention, because this is absolutely something to keep in mind. Anyhow, the situation has been vastly improved by increasing the speed. Let's change the mineral filler. Now, what happens if we move to wollastonite? Wollastonite is a completely different filler. As you've seen, it's a kind of, it seems a bit like a mineral glass fibers. The quality of the surface is terrible. At low speed, you have a very dull and rough surface. It's actually very coarse. You can really fit it under your fingertips. It's really terrible. With the same speed of the talc you have seen before. If we increase speed, you have an improvement, of course. But if you increase your speed too much, what happens is that you have flashes, because you have somehow increased too much the speed. The material became too liquid and it was squeezed between the two halves of the tool. Flashes are a main issues, not only from a surface finish point of view, but also from a technical point of view, because you have to deflash your part. Otherwise, it will be impossible to sell and to use it. And deflashing can take an overwhelming amount of time, and you want to stay away from flashes. Please keep this in mind, especially when it comes to material, very fluid materials like liquid crystals or PPS. Especially PPS is a material which is very prone to flashes. So pay attention if you want a perfectly looking part made out of PPS, like 40% glass fiber filled PPS, because if you increase the speed too much or temperature too much, you will have tons of flashes, which is a terrible issue. We have the same situation here, but with the submarine gate. You have always a very dull and rough surface, which is somehow improved by increasing the speed. And if you increase the speed too much, you do not see that kind of issue that you have seen before. You do not see the flashes, because this specific injection system will somehow reduce the speed of the material filling the cavity. So you somehow reduced also the applied pressure, and you will have an overall good looking part. Also with wollastonite. So the trick here is to increase the speed and to keep under control the speed of the melt into the cavity and applied pressure by using a properly designed injection system. The last filler, kaolin. Kaolin, as I told you before, is a nice filler, but it is quite difficult to properly disperse into the matrix. So it somehow pops out of the matrix. It can create a lot of issues. So you see the surface here with low speed is dull. You have a very bad looking spot around the fan gate. The situation is, of course, somehow improved around the edges by increasing the speed, but you can see how it got worse, extremely worse, close to injection location. You have a very bad looking spot and a dull surface as well. If you increase speed, you have some kind of improvement, but you cannot actually say that you are satisfied with your design of experiment. You still have a bad looking part. So the question is, are we going to surrender to the poor dispersion of kaolin? No, No, sir, because you remember that this is a design of experiment, so we still have a very important parameter to tune, which is the tool temperature. And we will see how it works in the next slide. This slide is just to focus your attention on the fact that by using a 3-gate injection location, you still have the same problem. I mean, it is even worse because you do not have only very bad looking spots and a dorsal and a very opaque surface, but you also have terrible weld lines. Terrible weld lines. You can see how evident they are here. Even at high speed, you have the most terrible, I would say, weld lines and a totally unacceptable surface finish. Let's see what happens if we work a little bit with our tool temperature. Let's raise the temperature of the tool just by 10 degrees C. Remember, we fixed the temperature of the tool at 90 degrees C. We just moved it to 90, from 80 to 90. So it's just 10 degrees C more. And you can really appreciate how the situation will somehow be solved by helping the material to properly flow and to properly disperse the filler. You see an improvement here. You can still see some streaks here and there, some kind of stains here and there, but the situation will be, I would say, acceptable. It's not perfect, but I mean, it is absolutely acceptable when it comes to high speed and high temperature. So remember that to properly work on the surface finish of your part, you can work with the mold temperature as well as the injection speed. So in this very case, we wanted to play a little bit with the tool temperature, and it is evident how it was possible to improve the surface finish even of the worst guy of all, which is kaolin. Now let's talk about the same design of experiment, but with a very, very, very popular plastic, which is polyamide-66 50% glass fiber. Typical metal replacement plastic, structural, high performance. It's very popular, used since the 80s, since the 70s. So it's a very long story. Today we have plenty of different variation on this formula. We have self-lubricant, flame retardant. You can see on the market plenty of. There is a lot to offer. Glass fibers are molten glass, which is spun into very, very thin fibers, which are chopped as chopped strands. These chopped strands are dispersed into the matrix, but it is not so easy to disperse it. And more than everything, they will provide a very bad looking surface on ordinary injection molding general purpose polyamide-66 50% glass. Let's see what is the difference in the surface finish, so in the aesthetic of your part, by using an ordinary general purpose polyamide-66 50% glass and another formula which has been tuned from a matrix point of view in order to boost, to increase, to improve the quality of the surface finish. Remember, this is a design of experiment, so we are allowed to tune all the parameters of the tool, of the injection system, of the injection parameters, and the material in itself. So in this very case, we start with two different formula. This is the typical surface finish of a 50% glass fiber general purpose, so that kind of material that you can use for more or less everything. Low speed with a 3 submarine gate. The surface is the worst you can actually imagine. This kind of surface will not only provide the idea of a bad looking part, but it will also provide the idea of a poorly performing part, because you have a lot of wrinkles and ripples, which can actually be perceived as cracks, as defects. So nobody will ever want to deal with such a plastic part. And you need to solve this surface finish issue before releasing your part on the market. Let's see what happens if we use the other formula, which has a different matrix. It's always a nylon 6/6, but it is somehow tuned to have a better surface finish. You can see that the surface is absolutely more acceptable. even if the quality of the surface finish is exactly the same. You still have some marbling, but the quality of the surface is much better. It is still not acceptable, but it is somehow better. The same is happening also in the case of fan gate, because the problem is not only the injection location, it's in the formula in itself, it's in the speed, in the process, and so on. You have some roughness and some spots. The same is observed also on the improved finish proposal. You still have some very poor surface. Let's try to increase speed. What happens if we increase speed? There is no solution of the problem on the three-gate submarine part, but you can see how relevant is the improvement with the other solution, with the improved finish solution. You can actually start to see the reflected shape of our technician in the bowl in itself. It means that the quality is really improving. It's not still perfect, but it is somehow improved. We still have some flashes here and there and some streaks, but this part is more or less acceptable. The same is achieved on the fan gate. There is some improvement also in this case. Not looking as good as the previous solution, but it is somehow more acceptable. So what we see here is that you can achieve a good looking part, keeping the same injection location, keeping the same molding condition, just tuning the material, which is the material formula, which is one of the parameters that we are somehow allowed to do. What happens with high speed? You see it here. The standard grade is always bad looking, always poor looking. There is no way to improve this kind of typical formula, but the improved finish formula, which is tuned in the matrix part, is absolutely glossy and very good looking. Not only with the three gates, but also with the fan gate. And you see it here. Also in this case, you have a much better performance from a surface finish point of view when it comes even to the fan gate. So the conclusion of this specific part of our design of experiment is that with some formulas, there is no way to improve it just by tuning the speed. You have to somehow tune the formula of the material as well, as in this case. Now, we are at the end of our webinar. We are going to talk about what happens with the amorphous plastics. First of all, we have to focus our attention on the main difference between amorphous and semi-crystalline, not only the morphological, but also the thermal point of view. The semi-crystalline plastics have a glass transition temperature range, which is set by the formula of the polymer itself. And we must keep an eye on this glass transition temperature because we want to set the mold temperature of our tool 10, 20, 30 degrees above this temperature, because if we want to have a very good looking part. What happens with amorphous plastics? Amorphous plastics have a much narrower glass transition temperature, and we want to stay as close as possible to this temperature. Actually, it is recommended to stay 20 to 30 degrees C above when it comes to semi-crystalline. It is recommended to stay more or less close to the glass transition temperature for the reason that we are going to find out right now. The point is that it is not normally, polycarbonate is not molded at 150, it's molded with 100 something. Let's see it with our design of experiment. So we picked up a polycarbonate thread, 30% glass fiber filled, and we wanted to inject it at low speed and then moving the speed, but with two different temperatures, 40 degrees C and 100 degrees C. Here is how it looks like with 40 degrees C, extremely bad, very rough, very marbled, terrible looking part. So totally unacceptable. This is how it looks with 100 degrees C. You see it is the gloss is vastly increased, and it is really improved, I would say. You still have some spots here and there, but you have a relevant effect of the tool temperature. Remember what we have seen with the polyamide 6 with kaolin, how relevant was the effect of the tool temperature actually. Let's try to increase the speed. Let's see what happens if we put more energy in the melt, if we put more stress in the melt plastic. For the for the picture on your left, 40 degrees C tool temperature, you still have poor looking part, evident weld lines, very rough surface, totally not acceptable. But you can really appreciate an impressive improvement on the part molded with 100 degrees C. You put more energy in the tool and in the melt. And we will see what happened with high speed. You will see definitely improvement. With high speed, you always have a poor looking part if you keep the temperature of your tool too low, but the surface finish of your part will be almost perfect if you use high speed and high temperature. I strongly recommend to keep high temperature when it comes to amorphous plastics, even semi-crystalline plastics, but amorphous are extremely sensitive to the tool temperature, because if you keep a low temperature of your tool with polycarbonate, you will promote the impact resistance of plastic, but you can somehow mold some stresses in. It's something that should be avoided. Always rely on the instructions that you can see on our technical data sheet. So, all in all, this was the end of our webinar. We have to somehow wrap up all the topics that we have been discussing and what we have seen right now. We have seen a design of experiment. We picked up a few different formulas. We tried to differentiate the formulas in itself, then the molding condition, the tool setup, the injection speed, and the tool temperature. And we saw how different can be the effect of each one of these parameters on the result of the surface finish. So, if we want to have if you want to summarize what we have been discussing till now, aesthetics is a compromise. You cannot have a super performing part and a super good looking part. Everybody wants it, but it's not so easy. You have to accept a compromise. First of all, the part geometry. The thickness of the walls will play a major role in the quality of your part. Low thicknesses promote high shear stress, high temperature, so they can look much more glossy, but they can also promote material degradation. High thicknesses will promote sink marks, and you will have a slowing in the melt diffusion during the filling part, and this can create bad streaks on the surface. So the part geometry is the relevance of the part geometry is dramatic. You want to keep the thickness of your walls as homogeneous as possible in order to have more or less the same surface finish all over your part. This, of course, is strictly related with the tool design in itself. The design of the tool must keep into consideration this topic and must, of course, keep into consideration also the draft angle and the way you want your part to perform. The material is selected at the very beginning, but each material will somehow provide its own surface finish. So it is not possible to have fully carbon fiber field with Teflon inside, or a 65% glass fiber field looking like plain ABS or polystyrene or stuff like that, because they are completely different material. Each material, each formula is providing its own blueprint, its own watermark, let me say, on the surface finish. Of course, you have to pay attention to the molding parameters. We have been discussing this during our webinar. Molding parameters play a major role: mold temperature, barrel temperature, injection speed, but also the packing pressure and packing time. These all can provide their contribution to the quality of the surface finish. So there is a very strong relationship between all these parameters, and you have to look for a good compromise. My personal recommendation is, of course, to always get in touch with your material supplier, who will be able to give you the best suggestions, also to solve not only surface finish issues, but to find this compromise, which can be actually very tricky, especially when you have a very complicated part with some cooling difficulties on the tool, promoting glossy spots here and there, or some kind of distortion. Rely on your supplier. Suppliers normally will provide plenty of technical skills and know-how to help you reach the best compromise. I really hope I was able to give you a decent introduction to this design of experiment, which was more fun than the normal theory of plastics. I really hope you will enjoy also the other webinars that LATI is going to offer. The next one will be about sustainability and circular economy, but not from a, let me say, orthodox point of view. We'll try to be a little bit groundbreaking on this very relevant topic. So I thank you, and I will welcome your questions, if any. So if you have any question, just put it in the chat box, and I will be happy to answer within a couple of minutes. Okay, there is the first question is concerning any chance to simulate this with computer finite element analysis and computer simulation in general. Finite element analysis and computer simulation has become extremely reliable and extremely complicated and extremely, I would say, skilled, also in detecting, I would say, not physical related aspects as aesthetics. Our softwares that you can find on the market will, of course, tell you where are the weld lines, will tell you a bit more about the quality of the weld line, will also tell you about the sink marks, but you cannot not have a, let me say, a really reliable forecast of how your part will look like, because it is more related to the experience of the tool maker and the material producer in itself. So use your simulation to detect any sink mark issue or stuff like that, but then you need some trial and error, some design of experiment to have a proper solution about this. Okay, the next question is concerning why do you need aesthetics on technical parts? I told you at the very beginning of my webinar, because even in the technical sector today, you have the perception of a good looking part as that of a properly working part. If you see a bad looking part, the perception you have is that this part may not work fine, that something happened during the molding cycle of this plastic. And you may be right, because normally a bad looking part, a wrinkly surface, ripples here and there can promote cracks, can promote mechanical failure. So actually a bad looking part normally is telling you that something happened also during the, let me say, also during the molding cycle or the life of the plastic in itself. So yeah, the answer is yes. Even for under the bonnet application, we have plenty of requests for perfectly looking part. And this is funny, and even from customers working in the electronic industry, for fuse holders, for parts that no human eye will ever see once the device is closed. Customers need the perfectly looking part, because color matching is not the only problem. They want no streaks, no sink marks, they want no kind of glossy spots here and there. So aesthetic and surface finish is mandatory more or less on any kind of plastic. Which materials do not allow this kind of glossy or perfectly looking part? Normally, I would say that some flame retardant can be an issue because flame retardant formulas are filled quite a lot. And even some self-lubricants can be a problem with PTFE. PTFE can create some streaks on the surface, whitish streaks on the surface of injection molded parts. Carbon fibers as well can be a problem. It is not so easy to have a perfectly looking carbon fiber filled part. And steel fibers as well. Steel fibers cannot provide a very nice looking part because of they are not properly, I would say, dispersed or mixed into the matrix. So you will always see this salt and pepper surface and they do not look good, but they are very functional. So there is no way to turn around this kind of issue. Okay, I think we are running out of time. If you have any other question, please drop me a line. You will find all my reference in this slide here. You can ask myself, Luca Posca, or my colleague Rinaldo Zanasca, who had this webinar in Italian this morning. Just drop a line at the info mailbox on our LATI website, and we will be happy to provide any kind of answer about materials and surface finish that you may ask. I strongly encourage you, invite you to keep track of what's going on in LATI and our webinars, of course, and keep an eye on the news on our website, because you will find plenty of very interesting tips. Soon to be released, a complete detailed guide to surface defects. It will be released during year 2023. I thank you for your time, thank you for your attention, and look forward to meeting you in the forthcoming webinars. Have a nice day, have a nice evening. Bye-bye.